Imagine a snowball from another sun threading the dark between stars. No home port, no return ticket, just a long, silent fall across light years until it appears in our sky and does something our rulebook politely says it shouldn't. At nearly 3 times the distance of Earth from the sun, where water ice is supposed to be stubborn and sleepy, this traveler coughs out a bright, wet breath. A vast, ghostly halo blooms around it. The numbers say, "Too cold for that." The images say it's happening anyway. And suddenly the astronomy blogs and coffee room debates are humming with the most human of sentences. Wait, what? We named it 3I divided by Atlas, the third confirmed interstellar object ever seen in our solar system. That 3I tag is both a scientific badge and a narrative burden, because number 3 changes the story. 1 could be a fluke, 2 could be a coincidence, 3 starts to look like a pattern, or at least a pattern of surprises. First came a dry, tumbling shard that refused to behave like a normal comet. Then a textbook comet, dusty and gas-rich, like an emissary from a familiar winter. Now this, an object that brightens early, exhales water far from the comfy, warm zone, and invites the question we'll spend this film chasing. What if 3I divided by Atlas isn't what we think it is? Picture it as an animated sequence. Space is ink black and full of tiny, patient stars. Our traveler enters from the top of the frame, a speck with a long, soft veil. Labels pop into view: distances, temperatures, a dotted curve showing its path. A narrator, that's me, reminds us of the rules. Water ice likes warmth. Comets usually wake closer in. Light curves, the way brightness changes, tend to follow a script written by sublimating ices. The speck crosses an invisible boundary where the script says the curtain is still closed. Instead, the curtain lifts. The halo grows. The tail lengthens as if someone turned on a faucet in deep winter. Cut to the control room of a small observatory. Screens glow blue with spectra, those thin rainbows scientists use as fingerprints of what a thing is made of. A line deepens where hydroxyl should be. Someone leans forward. A keystroke. A breath. A second observation. A third. The line is still there. Out in the world, headlines do their headline thing. Interstellar visitor spouts water far from Sunday. Tweet threads bloom with theories like frost on glass. In classrooms and lab meetings, the tone is more careful, more interesting. Okay, suppose that's true. What does that mean? It means we might be catching physics in the act, chemistry and sunlight negotiating in a place we haven't watched closely before. It means our categories, asteroid, comet, icy, rocky, are not sacred truths, but helpful guesses that work until they don't. It means that if you zoom out far enough, even a single breath of water at the edge of comfort can redraw a map. But the deeper question is older and bigger. When something from far away behaves oddly, do we rename the thing or rewrite the rules? Do we label the outlier as weird and move on? Or do we let it tug at the threads of our certainty until the whole sweater of how comets behave looks different? If you've ever stared at a cloudy bathroom mirror and traced a finger through the fog, you know how steam reveals patterns that were invisible a moment before. 3I divided by Atlas is like that finger. Its early halo is a line through our fog, revealing a hidden shape. Or maybe just teasing one. It's not just about water at the wrong distance. It's about why that water is there, how it gets out, and what story that tells about the place this object was born, a star system that has never and may never know we exist. And there's another layer, the clock. Interstellar visitors are in a hurry. Their paths are steep, their stays brief. If you were designing a mystery to torment curious primates with telescopes, this is the one you'd choose. Something that arrives with anomalies baked in, dares you to solve them, and then leaves before you've finished your coffee. We have a narrow window to watch. 3I divided by Atlas shout into vacuum and read the echo. So, here's our pact for the next couple of hours. We'll suspend easy labels and chase possibilities. We'll test the simplest explanations first, because nature is a master of doing strange things with ordinary tools. We'll entertain wilder ideas not because we need them, but because they help us design better tests. And we'll keep our eyes on the horizon where science meets meaning. Because whether this object turns out to be a very weird comet or something without a good name yet, it's a mirror. It reflects our habits of thought. How quickly we name, how slowly we doubt, how attached we are to the comfort of categories. What if 3I divided by Atlas isn't what we think it is? Maybe that's the wrong way to phrase it. Maybe the real question is, what if we aren't thinking about it the right way? Start with the scoreboard. In all of human history, we have confirmed exactly 3 objects that were born around other stars and then wandered into our neighborhood. 1I, ʻOumuamua, in 2017. 2I divided by Borisov in 2019. And now 3I divided by Atlas. That's not a data set, that's a rumor. And yet even a rumor can rattle the furniture if it's loud enough. Each of these visitors has told a different story. A dry, tumbling enigma, a classic, gas-rich comet, and now a traveler that breathes water earlier than our comfort zone likes. If you're writing the textbook, that's not a paragraph, it's 3 footnotes arguing in the margin. Why does it matter? Because interstellar objects are care packages from other solar systems. They are the crumbs that fall from other planets' kitchens, bits of ice and rock shaped by alien winters and summers, by suns that flare differently, by giant planets that kick their leftovers into space with different rhythms. When one of those crumbs lands on our porch, we get to unwrap a piece of someone else's origin story. In a universe where direct images of young worlds are rare and blurry, that's priceless. Now zoom in to the present tense. Our telescopes are finite, our time windows narrow, and our questions greedy. We want to know, what is 3I divided by Atlas made of? How big is the nucleus inside that luminous shroud? What's driving its activity at those distances? Carbon monoxide, carbon dioxide, water hitchhiking on bigger grains, or something we didn't plan for? Does its path betray tiny pushes from outgassing jets? Are there fragments peeling off, whispering that it's fragile? Every answer plugs into a larger machine. Models of how planetary systems build comets and then eject them into interstellar space. Get the chemistry wrong, and you misread the climates of other suns. Get the dynamics wrong, and you mistake a shove for a law. There's also the reputational stake, less cosmic, very human. The first interstellar guest sparked fierce debate about what counts as natural. The second seemed to soothe nerves. Okay, it's a comet. We know this dance. The third arrives and immediately breaks choreography again. Science loves surprises, but institutions love stability. Funding, observation time, and public interest pivot on whether we can frame a tidy story. If 3I divided by Atlas refuses tidy, then the brave choice is to follow it into untidiness, because that's where real updates live. Think of the practical ripples. If early activity can be driven far from the sun by volatiles we don't usually catch in action, then our search scripts might be missing a class of faint, prematurely active visitors. Survey pipelines tuned for a certain brightness curve could be undercounting the universe's mail. More interstellar objects might be slipping past simply because they don't behave like the ones we trained on. In other words, 3I divided by Atlas isn't just a mystery to solve. It's a calibration tool. It could teach us where our instruments, algorithms, and assumptions are deaf. And then there's the philosophical stake. We like to think categories are discovered, not invented. But out there, under the indifferent starlight, comet is a convenience more than a truth. The cosmos never signed our paperwork. If 3I divided by Atlas forces us to redraw the borders of that word, if it expands comet to include behaviors we used to call improbable, then we've grown a little. Not because we nailed the label, but because we made the label softer, more honest, more porous to reality. Finally, a clock tick you can feel. Interstellar objects do not linger. They cross our stage at steep angles, with exit routes already planned. The stakes aren't just abstract, they're urgent. Observatories juggle schedules to squeeze in spectra and images before the light fades. Teams collaborate across continents not because it's tidy, but because it's now or never. If we get this right, if we listen carefully while the visitor sings, then for years afterward, every model of planet formation, every survey design, every freshman lecture slide on what is a comet will be a little closer to the universe and a little farther from our habits. That's what's on the table. Not a single oddball, but a lever. Push here, and our picture of other suns tilts. Start with the orbit, because the path is the prologue. 3I divided by Atlas is not bound to our Sunday. Its track is hyperbolic, an in-and-out sprint through the inner solar system, so by definition it is a visitor from elsewhere. Discovery threads back to the 1st of July 2025, when the Atlas survey in Chile flagged a moving smear that didn't fit the local family tree. Follow-up made the case. Eccentricity above 1. Speed and angle wrong for a native. Coma already glowing. That's how the 3I tag arrived. The third interstellar object after ʻOumuamua, 1I, and Borisov, 2I. A calendar as well as a map. The object swung through perihelion around Oct 2930, 2025, inside Mars's orbit at roughly 1.361.4 AU, then continued outbound, never coming closer than about 1.8 AU to Earth, comfortably distant, scientifically delicious. On the way in, it skimmed by Mars in early October. On the way out, it gives wider passes to Venus and Jupiter. None of this is threatening. All of it is useful. The geometry set up a months-long observing campaign, spread across hemispheres and instruments. Then there are the pictures, the kind that shift a debate from maybe to okay. Let's quantify. In late July, the Hubble Space Telescope resolved a classic cometary teardrop, dust peeling off the sun-facing side, a radiation pressure tail sweeping back. From that coma morphology, Hubble teams inferred a compact nucleus likely no more than a few kilometers across. It's not a monolith the size of a city. It's an icy core small enough to be hidden by its own breath. That breath, however, is the headline. The headline came from a kind of light our eyes can't see. Swift. The Neil Gehrels Observatory that hunts ultraviolet signatures picked up OH, hydroxyl, a reliable tracer of water, H2O, when 3I divided by Atlas was still roughly 2.9 AU from the Sunday. Translate that into kitchen sink terms, and you get flow rates on the order of 240 kilograms per second. Not the biggest outburst ever, but startling at that distance, where water ice is supposed to be mostly asleep. The UV lines were clear enough to survive repeated checks and skeptical eyebrows. Even better, they landed alongside hints that CO2 might be unusually abundant relative to water, a clue that colder, more volatile ices could be running the show and lofting water-rich grains along for the ride. So, the snapshot so far looks like this. A smallish nucleus wearing a bright coma, venting gas and dust far from the warmth we usually associate with water-driven comets. We are watching a familiar phenomenon, sublimation, play out in an unfamiliar regime. That contrast is what bends the learning curve upward. But no in science always arrives with error bars. How big is the nucleus, really? Hubble's upper limit, a few miles across, comes from how much dust we see and how sharply the inner coma fades, not from a clean silhouette. Models that convert coma brightness into mass loss depend on particle sizes, shapes, and speeds. Change those, and your nucleus estimate breathes. That's why observers chase the same target in different wavelengths. Thermal, infrared to feel the dust, visible light to weigh the reflection, ultraviolet to sniff the gas. Each channel adds a constraint. Each channel also adds a caveat. On composition, the ground is firmer than rumor, but still soft. The OH detection gives high confidence that some water is entering the coma well before the inner solar system. The leading natural explanation is not hot water far from the sun, but other volatiles doing the heavy lifting. CO and CO2 sublimate at lower temperatures than water ice. If 3I divided by Atlas is rich in those, they can blow off dust and embedded ice grains even in the cold, creating the appearance of water waking up early when the driver is actually something else. Spectroscopy that isolates CO and CO2 bands becomes the arbiter here, and teams have been racing to measure how those ratios evolve with heliocentric distance. Early reports point to a relatively strong CO2 divided by H2O story, consistent with that picture, but the detailed curve with distance is what will tell us which tap is really open. Dynamics are the other half of the ledger, because a venting comet is also a thruster. When gas jets push off a nucleus, they can impart tiny accelerations that nudge the object off a purely gravitational path. We've seen that movie before with garden variety comets and argued about it loudly with ʻOumuamua. For 3I divided by Atlas, the question is whether the astrometry, those precise position measurements night after night, shows systematic, reproducible deviations that line up with its activity cycle. If so, we'll need non-gravitational terms in the orbit fit. If not, gravity wins, and the jets are either symmetric or too weak to matter. Either answer is informative, and either answer still leaves 3I interstellar because the hyperbolic energy is far too high to be faked by outgassing alone. Scale the camera up from the nucleus to the whole sky, and you see a second surprise. The trajectory lies close to the ecliptic, our solar system's disk plane. That alignment has fueled more headlines than it deserves, but it is observationally true. The incoming path is retrograde and only a few degrees from our planetary sheet. Statistically curious? Maybe. Impossible? No. It's a large sky. Occasional alignments happen. Still, the geometry was a gift. It let Mars orbiting and Earth orbiting assets both get good looks and set up a clean perihelion campaign as the object cut across familiar constellations. We also know a little about what it isn't. It isn't inert rock masquerading as a comet. Multiple instruments have seen gas and dust. Hubble literally resolves the coma. Swift reads water's UV echo. There are no glints of specular reflection that would hint at flat, engineered surfaces. And no narrowband radio beacons riding along with the sunlight. The mainstream read is natural and icy, with unusual ratios and timing. Fringe speculation exists. This is astronomy in the social media era, but it has to climb a steep hill of ordinary physics, already matching most of the facts. What about size claims largest, oldest, ancient shard? Here, the honest answer is, we don't have a single, locked number. We have upper limits from Hubble, photometric estimates that depend on albedo and grain models, and gas production rates that vary with time. Could the nucleus be a kilometer class? Yes. Could it be several? Also plausible. The key is that even a few kilometer body can produce tens of kilograms of water per second if the surface is active, or if loose chunks are being shed and sublimated in the coma. That's why some researchers talk about a rubble pile, a fragile aggregate whose own debris contributes to the illusion of a giant water tap. Hubble's images of asymmetric, sun-facing dust emission are consistent with a body that's waking unevenly as it rotates. There are two other anchors worth pinning down before we chase hypotheses. First, proximity and risk. Even at closest Earth approach, 3I divided by Atlas stays dozens of times farther than the Moon, and it never crosses an Earth impact geometry. This is a science story, not a disaster movie. Second, observing cadence. Because the object brightened earlier than expected, some facilities caught it on inbound legs they might otherwise have skipped. That's a quiet triumph of modern survey work, algorithms, and small scopes, handing off to big mirrors and space telescopes without losing the thread. That is the ground we can stand on without reaching. The poetry comes later. The discipline is right now. Because each bullet above seeds a test. If CO2 is the engine, spectra across distances should map that throttle. If rubble pile shedding is real, the light curve should carry the fingerprints of clumps and spin stochastic brightening, subtle color changes, evolving jets. If non-gravitational pushes matter, the orbit fit should noticeably improve when we include them. One more piece of context helps you feel the stakes in your bones. We are not just cataloging a weird comet, we are sampling planet formation by proxy. Interstellar objects are what happens when giant planets and disks roughhouse, when material is scattered outward so hard it leaves home forever. The ice inventories, grain sizes, and isotope ratios in these objects are handwritten notes from someone else's protoplanetary disk. 1I, 2I, 3I, 3 notes, 3 very different handwriting styles. That diversity is already a discovery. The so far in what we know so far isn't a shrug. It's a promise. Keep watching, and the pattern behind the surprises will sharpen. Think of a freezer that opens before you touch the handle. That, in plain language, is the heart of our first idea. Maybe 3. I divided by Atlas wakes up early not because its water ice is hot, but because other ices, ones that get lively in deeper cold, do the lifting. They turn on first, blow dust and little snow grains off the surface, and those tiny passengers carry water with them. From far away, it looks like water is in charge. Up close, it's the cold-loving stuff doing the work. Let's make this less abstract. Picture the nucleus, an irregular lump, dark as charcoal. Sunlight warms it, but not much. Deep inside, you have layers of different ices, like a cake made by a chemist. Some layers need a lot of heat to soften. Some need only a hint. If the easy layers are near the surface, they'll fizz first. They'll push gas through cracks and vents, like steam through a kettle spout, and that push lifts dust and frost off the skin of the comet. Now, if some of those lifted bits are water-rich grains, mini snowballs, then the sunlight can nibble at them while they're floating in the halo. You don't need the whole comet to be warm. You just need these tiny grains to be small enough and bright enough that they heat up quickly, whisper out their water, and make the halo glow in ways that scream, "There's water here." That's the magic trick. Water shows up early without being the one turning the crank. If that's the engine, what should the story look like from Earth? First, you'd expect the comet to turn on farther out than we're used to. The switch flips at cold distances because the cold-loving ices can't help themselves. Second, the halo might look slightly different, more powdery, more full of floating specks that were yanked free and are now fading like breath on a window. Third, as the comet comes closer to the sun, you might see the rhythm change. The early driver hums along, but the water joins the choir later, getting louder and busier as the trip warms up. All of that is human speak for a simple picture. The faucet opens early, but it isn't the faucet we're used to watching. What kind of landscape would build a comet like that? Imagine a solar system colder than ours, or a very deep freezer at the edge of any system, an outer belt where sunlight is weak and winters last longer than civilizations. Out there, different ices can pile up near the surface because nothing melts them away. Over millions of years, slow chemistry and slow snowing can leave you with a crust that's more eager to breathe in the cold. If a giant planet kicks that crusty body into the dark and it wanders for ages between stars, it carries that personality with it. When it finally stumbles into our light, it behaves like the world that raised it. Early breathing, cold-triggered, odd. This idea also explains why the comet can look so busy without being very big. If gas is pushing off dusty clumps and mini grains, each of those grains becomes a tiny comet in its own right for a few hours or days, warming, venting, fading. One nucleus becomes a cloud of helpers, and the total breath you measure is the sum of 1,000 small voices. That's why modest objects can fool our instincts. The halo's brightness isn't just from the core, it's from the swarm. And swarms have moods. They can pulse. They can brighten faster than a single, smooth surface would. If 3I divided by Atlas is fueled by this cold first engine, the light we see from night to night might flutter like a candle in a draft steady overall. But with little flickers when a vein opens or a soft patch gives way. In images, the tail might look feathered, not razor straight. The sunward side might have soft moth-wing textures where fresh grains are born and blown back. There's a lovely humility in this. We're not proposing alien technology or rewriting physics. We're saying, what if nature is doing the usual thing, just rearranged? The same Sunday, the same kinds of ice. But the order they wake up in is different, because the recipe is different. It's like biting into bread you've eaten 1,000 times and tasting cinnamon before the butter. Nothing new was invented. The timing of flavor changed. This exotic ice engine also gives us a gentle way to read the early water signature without forcing the comet to act hotter than it is. The water isn't roaring out from deep caves. It's leaking from dust, snowflakes that were carried into daylight. That matters because it keeps our picture honest. We don't have to make up a reason for water to ignore the thermometer. We just have to remember that small things warm up quickly and that sunlight is patient. So how might this play out over the full arc of the comet's visit? In the outer months, when the sun is a pale lamp, the cold-loving ices run the show. They open vents. They lift dust. They create a halo that already whispers, wet. As the comet dips into brighter light, the water joins in more directly. The exhaust gets denser, the halo thickens, the tail grows meatier. If the surface is patchy, and most small worlds are, you'll get hot spots that turn on and off as the comet spins, like streetlights in a fog. There's a deeper, almost narrative satisfaction to this idea. Our minds like clean categories: on divided by off, dry divided by wet, dead divided by alive. But small icy bodies don't care about our bins. They wake in phases. One layer rouses another. One kind of ice carries a friend to the party. The exotic ice engine is really a story about order. Which part of the comet gets a say first? In 3I divided by Atlas, the early voice might belong to the cold. If you're the person at the telescope, what do you look for without drowning anyone in alphabet soup? You watch the mood swings. You see whether the comet's breathing is smooth or twitchy. You look for changes in color that say, more dust today, less dust tomorrow. You pay attention to whether the halo looks thicker on the sun-facing side, like frost, and whether that bias changes as the comet spins. You note how quickly it brightens as it falls inward, and whether there's a gentle handoff from early driver to water joins in. None of this requires you to memorize the names of specific colors of light. It's pattern-watching sky weather. And if the exotic ice engine is wrong, that's useful too. If the comet's brightness refuses to follow that handoff, if the early activity doesn't settle into a smooth rise, or if the halo looks heavy with big chunks instead of fine dust, then another story is better. Science is generous like that. Every wrong guess, clearly tested, makes the next guess sharper. But let's indulge the picture for a moment and imagine it is right. What does it mean beyond this one object? First, it stretches the word comet without snapping it. We don't have to invent a new category. We just widen the doorway to include more behaviors. Second, it tells us that other solar systems likely stock their freezers differently. They bake comets with different layers near the surface. Some will be early talkers. Some will be late bloomers. Third, it hints that our surveys might be biased. If we trained our eyes to spot comets that wake up close to the sun, we might be missing a population that whispers earlier and fainter, then leaves before we realize what we saw. There's also a quiet, hopeful message about habit. We humans love to chase the flashy answer. You can feel the pull of, "It's a spacecraft," in your bones. But most of the time, the universe prefers simple ingredients artfully arranged. The exotic ice engine is that kind of elegance. No new physics, just a different order of operations. It asks us to slow down, to let a familiar set of tools surprise us. Picture our animated comet again. Far from the sun, small geysers open. Dust and frost lift, drift, and glow. The halo's light is soft, like chalk dust caught in a projector beam. As weeks pass, the glow thickens. Patterns on the sunward side sharpen. The tail lengthens until it looks like a brushstroke on black velvet. In a control room somewhere, a tired observer sips cold coffee and smiles at a graph that just got a little smoother. The early whisperer has handed the microphone to the louder singer, right on cue. And if you're watching at home, what should you take away without a single equation? This, 3I divided by Atlas, may be surprising us not by breaking the rules, but by following a set of rules we rarely get to watch. It's like catching a play from the back of the theater and finally realizing there was a first act you'd been missing. The stage lights didn't brighten. Our attention did. Last, a note on humility. Even if this idea fits beautifully today, the comet reserves the right to misbehave tomorrow. A crack can open. A patch can fall apart. A small fragment can peel away and steal the spotlight for a week. That's not the hypothesis failing. That's the character of small, fragile worlds. They are elbows and corners and sudden moods. Our job is to keep listening, and to prefer the explanation that earns its keep across many nights, not just one. So, Hypothesis A in one breath. 3I divided by Atlas wakes early because cold-loving ices light the fuse. Those ices lift dust and mini snowballs that let water reveal itself before the main act. The comet isn't cheating the thermometer. It's playing a duet where the quiet instrument starts the song. Hold a snowball too loosely, and it sifts through your fingers. Hold it too tightly, and it crumbles. Many comets live in that awkward middle, barely holding themselves together. Hypothesis B says 3I divided by Atlas might be one of those. Less a single solid stone, more a bundle of frosty crumbs, pebbles, and weakly glued slabs. In space, we call this a rubble pile. It's not an insult, it's a biography. Picture the nucleus as a lumpy patchwork husk. Sunlight rolls across it like a slow wave. Wherever it finds a weak seam, some dusty grout between icy rocks, the surface sheds. Not in cinematic explosions, but in small, steady giveaways. A handful of grains here, a chip there, and every so often, a larger clump that drifts free like a dandelion puff. Each of those escapees becomes a tiny world with its own weather. A walnut-sized chunk warms fast, vents a little, and fades. A pebble shows a faint halo for hours. A snowflake sublimates in minutes. Add up 1,000 of these small voices, and you get a big choir. To us, a telescope beam sees one bright breath, but it's really a swarm of miniature comets singing together. That's how a modest, fragile object can look louder than its size suggests. This picture explains the mood swings that observers love to argue about. A rubble pile doesn't brighten like a dimmer switch. It flickers. One night, nothing special. The next, a patch loosens. A clump peels off, and the comet looks a shade richer, the halo a little thicker, the tail textured with soft feathers. A week later, the music quiets again until the next seam gives way. If you graphed its brightness, the line would lean upward overall, but with little steps and hiccups along the way, like a heartbeat on a monitor. It also explains the shapes we might see. A smooth, solid body often vents from a few repeatable spots. A fragile, shedding body paints a softer picture. A broad, sunward glow that looks slightly fuzzy, as if lit by chalk dust. Tiny knots and streaks that drift and smear over days. A tail that sometimes looks combed, sometimes rumpled. Nothing is perfectly sharp because the source isn't a single nozzle. It's a crowd. Where does a rubble pile come from? Time and violence. In the deep outskirts of a solar system, small, icy bodies collide gently for millions of years, sticking into bigger clumps. Later, they get nudged inward or outward by giant planets. Some break during flybys. Some crack from repeated warming and cooling. Some spin up until they loosen like a tired screw. The pieces regather under their own small gravity, never melting into one fused block, just settling like gravel in a jar. Then, a final kick tosses the jar into the dark between stars. By the time one of these travelers wanders into our light, it carries the scars of a long, rough childhood. If 3I divided by Atlas is that kind of survivor, a few human-scale images help. Think of a sandcastle after the tide has licked it for hours. It's still there, recognizable, but the edges have softened. Tunnels have collapsed. And little avalanches keep happening without warning. Or think of an old book whose binding has gone tired. Turn a page too quickly, and some flakes fall out. Turn the next page slowly, and it holds. Fragility isn't constant. It's a mood with memory. Now, what would this mean for what we notice from Earth without drowning in terms? First, we'd expect occasional jumps in brightness that don't care about our neat schedules, not wild fireworks, just small, real steps. Second, we'd expect color and texture in the halo to change subtly when fresh material is released. The light might look a little dustier one night, a little cleaner another. Third, the direction of the glow might lean toward the sun more strongly right after a shed, as new grains are born and immediately pushed away. Rotation adds spice. Imagine a clumpy top spinning in slow motion. As patchy faces roll into sunlight, weak spots warm and shed. When they roll away, things calm down. A rubble pile is full of such personality. Over many nights, this can draw a faint rhythm into the data. Not a metronome, but a heartbeat, irregular, but alive. There's a deeper, emotional reason this hypothesis resonates. It treats 3I divided by Atlas not as a hyper-competent machine following a perfect script, but as a tired traveler making do with what it has. That's a strangely human story. Flawed, resilient, always one warm afternoon away from coming apart a little and then carrying on anyway. It also gives us a gentle answer to the early water riddle without invoking complex chemistry. If the surface is constantly sprinkling small, icy clumps into space, sunlight can work on those clumps directly. They warm quickly and release a little water as they drift long before the main body would look hot by our standards. No special tricks, just lots of fragile confetti doing quiet work. Of course, fragility comes with consequences. A rubble pile can break. Sometimes breakups are dramatic, visible fragments marching away like a tiny flock. More often, they're subtle. A short-lived increase in brightness, a new smudge in the coma that smooths out over days. If 3I divided by Atlas ever sheds a true chip, we might catch a small knot sliding down the tail before it dissolves into velvet. If it doesn't, the absence is still a clue. Perhaps the surface is weak enough to shed dust, but cohesive enough to hold together at larger scales. One of the loveliest things about this idea is how it reframes risk and reward for observers. You don't need exotic instruments to notice a fragile personality. A series of careful images, spaced over weeks, can tell the tale. The slight day-to-day breathing of the halo, the softening and sharpening of edges, the timing of little upticks. It's patient work, like watching seasons change on a distant hillside. The drama is quiet. The plot is real. There's humility here, too, for all of us who love clean definitions. If this hypothesis fits, then what is a comet becomes less a box and more a spectrum on one end, sturdy blocks that vent neatly, on the other, loose assemblies that molt. Both are comets. Both are honest ways to be a small, cold thing under a big, hot star. And the meaning spills outward. If many interstellar visitors are rubble piles, then other star systems are not just forging perfect ice bullets and firing them into space. They're also shedding the messy leftovers of planet-building crumbs, not crystals. That says something kind about the universe. It's not curated, it's lived in. Creation leaves a trail of sawdust. What if the rubble pile idea is wrong? Then our next hypothesis earns its turn. Maybe 3I divided by Atlas is sturdier than we thought, and the early activity is driven by deeper vents and colder ices alone. Or maybe there's a mixture, solid core, fragile skin. The beauty of this process is that we don't need to choose a favorite for pride's sake. We follow the comet where it leads, and we let the simplest, most generous story win. Before we leave this idea, try one last picture. In our animation, we push in close to the nucleus. The surface is a patchwork of darker plates and lighter frost, stitched with hairline cracks. The sun crawls along the horizon. A sprinkle of dust grains skitters free from a ridge, hangs for a moment, then drifts upward on a breath so gentle you could miss it if you blinked. The camera pulls back. That sprinkle joins countless others, and together they become the luminous scarf we see from Earth. From far away, it looks smooth, serene, inevitable. Up close, it's made of little failures, each one a tiny release that keeps the whole from shattering. That's the tender logic of Hypothesis B. 3I divided by Atlas looks bold because it's fragile. Its beauty is the sum of small lettings go. Stand on a winter beach at night. The air bites. The snow under your boots isn't the fluffy stuff you get in town. It's wind-packed, salt-stiff, mixed with grit. You could scoop 2 handfuls of snow from 2 places and they'd feel like different materials. Now scale that idea up to entire solar systems. Hypothesis C says 3I divided by Atlas might be a shard from an exo-Kuiper belt. The cold outer pantry of some other star. Out there, far beyond the warmth, small worlds grow slowly out of frost and dust. But their recipe depends on the kitchen. How bright the star is, how often it flares, how many giant planets stomp around and stir the pot, what kinds of ices settle near the surface, and how deep the cold really goes. Change the kitchen, change the snowball. If our visitor was shaped in one of those distant belts, it would carry that place inside it like a passport stamp. Maybe its ice is stacked in different layers. Maybe gases that hide deep in our comets lounge near the surface in theirs. Maybe the dust grains are coated with different frost, or have sat in a cosmic deep freeze so long that their chemistry is a shade we rarely see at home. In short, it can still be a comet, just one raised under a different sky. Imagine the neighborhood it came from. Picture a pale star, a little dimmer than our sun, with a broad ring of debris at the edge of its light. Snow falls there in slow motion, not flakes from clouds, but a kind of space snow. Tiny shards that bump and stick, bump and stick. Every few million years, a bigger bully, an ice giant, say lumbers through and kicks some of the growing snowballs outward, some inward, and some all the way into exile. One of those exiles is our traveler. It drifts in darkness for lifetimes as long as continents. Then one day our sun grows from a star grain to a star coin, to a star that warms, just enough to wake old habits. The shard starts to breathe. If that's the origin story, a lot of 3I divided by Atlas's attitude makes intuitive sense. Early activity? Sure, if the top layers are stocked with ices that don't need much warmth to get frisky. A halo that looks powdery and generous. That fits a surface where dust and frost were stored loosely near the skin. Even the way brightness rises could feel different. The way snow from a dry climate crunches underfoot differently than slush from a late winter city street. Same element, different life. What would we expect to notice from Earth? Using only plain language, eyes and ears. First, the color of the dust might carry a hint of its upbringing. Some comets look a little redder or grayer depending on their mix of rock and frost and the sunburn they've endured. A shard from a harsher deep freeze could reflect light in a subtly different way. Nothing neon, just a tone that makes astronomers nod and say, not local. Second, the pace of its awakening might feel off compared to our usual playbook. A head start from the cold-loving layers, then a steady handoff as the familiar water ice adds its voice closer in. Third, the texture of the coma, the halo, could skew toward finer dust, like flour shaken from a sieve, if the surface was layered with fragile frost. Here's a human-sized analogy. Coffee. Beans grown on one mountain taste different from beans grown on another, even if you roast them to the same shade. Soil, altitude, rain. Neighboring plants' terroir soaks into flavor. Comets have terroir too. Their flavor is the sum of their home star's light, their giant's temper, their winter's length. When one wanders into our kitchen, we're not just tasting a drink, we're tasting a place. Why does this matter beyond poetry? Because each interstellar visitor becomes a sample return mission we didn't have to fly. We can't yet scoop dirt from dozens of alien systems, but every time a shard rushes through our sky, we get to sniff its breath and watch its dust and infer the weather of its birth. The variety we've seen so far, one dry and odd, one familiar and gassy, one a cold starter, already whispers that other solar systems don't all bake to the same recipe. If we collect enough of these whispers, they turn into a language. There's a larger curiosity hiding here: architecture. In our solar system, the Kuiper belt sits beyond Neptune, and a much more distant Oort cloud forms a sphere of sleepy comets. But around other stars, those structures can shift. Some systems might have fatter belts, richer in the ingredients that make cold starter comets. Others might have belts closer in, warmed just enough to rearrange which ices sit near the surface. Some might have giants that whip leftovers into space more often, filling the galaxy with exiles. We wouldn't know that from pretty pictures alone belts are dim and far. We'd know it from the personalities of the visitors who arrive at our door. If 3I divided by Atlas is an exo-Kuiper shard, it also reframes our expectations about what's normal. The mistake would be to treat our solar system as the default and judge everything else by how much it strays. Better to flip the arrow. Let strangeness be the starting point, and let normal be the center of gravity that emerges as we collect more cases. In that view, 3I divided by Atlas isn't misbehaving. It's performing exactly as a child of its home would. Our surprise is just provincial. There's even a soft echo of biology here. Life on Earth adapted to local rules. Salt marshes raise salt-ready plants. Deserts craft creatures that hoard water. Caves teach eyes to shrink and antennae to grow. Worlds do that too. A comet is a survivor of its environment. When it leaves home, it carries that environment like a fossil in motion. Watch it breathe and crumble and shine. And you're watching a long dead disk of ice and dust hold a conversation with our Sunday. What about the restless question everyone wants to ask but rarely does out loud? Could such a shard carry anything more than chemistry? The sober answer is that it's a messenger of conditions, not of life. But there's a deep connection between the two. If exobelts make comets with different ice mixes and delivery schedules, then different young planets will be fed different diets in their first millions of years. Some get extra water early, some get more carbon or nitrogen, some get almost nothing. Those early diets matter for seas, air, weather, and for whatever living chemistry might try to spark. So when we say 3I divided by Atlas tastes like a colder kitchen, we're indirectly talking about the kinds of planets that kitchen might raise. This hypothesis also helps us plan our future curiosity. If many interstellar visitors are exo-Kuiper shards, then to know the galaxy better, we should change how and when we look. Don't only stare near the sun waiting for comets to flare. Also peer deeper out, earlier in the approach, and listen for the quiet beginnings. Don't only chase the obvious show. Set aside time for the slow burn. In practical terms, design surveys that aren't biased toward late bloomers, and be ready to hand targets to space telescopes quickly when a visitor whispers from far away. Quiet equals early equals precious. And now the part where we make space for doubt. If 3I divided by Atlas turns out not to behave like a classic exo-Kuiper shard, if its accent fades as it warms, or if its dust looks more like our own stock, Maybe it's a hybrid, a traveler with a surface flavored by cold-loving ices, but a heart that acts like home. Maybe its kitchen had two chefs, a dim star at first, then a late-life brightening that rebaked the crust. Space is generous with maybes. Our job is to let the comet tell us which ones it earned. Before we close, bring the camera back to the image in your head. A dark stage, a pale star off-screen. Our visitor arcs across the frame, pulling a chalky veil behind it. In the voiceover, you hear a place whines and winters, and long silences speaking through powder and light. It's not just an object, it's an accent from far away. One sentence you can carry with you. An Exo-Kuiper shard behaves the way it was raised. If 3I divided by Atlas is such a shard, the surprise isn't that it wakes early. The surprise is that we expected anything else. Imagine steering a canoe by blowing on it. That's what comet jets do, tiny puffs that, over time, can bend the path a little. With 3I divided by Atlas, the question is simple. Is it gliding under pure gravity, or is its own breath giving it a slight shove? From Earth, we read this not with drama but with decimals. Night after night, telescopes take pinpoint positions and string them into a curve. If the curve refuses to sit perfectly on the gravity-only track, we nudge the model with a gentle push, like adding a steady wind to a map of a paper plane. If the fit gets better, the comet is pushing itself. Why it matters? A shove reveals personality. A smooth, balanced outflow gives little net push. A lopsided, pulsing outflow can act like a micro-thruster. That tells us about where the surface is active, how fast the gases escape, and whether the nucleus spins in a way that lines up or clashes with its jets. Picture a slow tumble. As a bright patch rolls into sunlight, a fan of gas turns on, and the canoe gets a tiny kick. Roll away. Quiet. Roll back. Kick. Over weeks, those kicks add up to a measurable bias. If we see that bias, we learn two things at once. One, the comet's breathing isn't perfectly even, and two, the timing of that breathing has a rhythm tied to rotation. If we don't see a shove, that's a result too. It could mean the jets are arranged like kids on a seesaw, balanced, or that the gas is coming off gently from many small places, pushing in all directions at once. Either way, gravity keeps the pen and the path stays clean. There's a humility in this test. It's not spotlight science, no fireworks, no dramatic pictures, just patience and good bookkeeping. But it's one of the few ways to learn about the nucleus without ever seeing it bare. A measurable nudge is the comet's silhouette in force form, an invisible sketch of how it lives and turns, and it ties back to everything we've said. An exotic ice engine could produce early directional puffs. A rubble pile could shed unevenly, swapping the direction of its pushes as weak spots move in and out of light. An Exo-Kuiper shard could carry surface layers that favor certain faces. The nudge is the chorus, note that tells you which soloist is singing loudest. In the end, we're not hunting drama, we're hunting character. A tiny shove, honestly measured, turns a bright dot into a living thing with habits and nudges us too toward better questions. Strange things invite shiny answers, a few headlines, a few odd behaviors, and the mind whispers, what if it's a ship? We should meet that whisper with kindness and standards. First, what would artificial even look like from here? Think mirrors and straight edges. Think glints that repeat like clockwork. Think radio signals that say, I am narrower than nature's usual noise. Think motion that ignores physics we expect, not by a hair but by a canyon. Turns without thrust, pauses without a cause. speeds that flip suddenly. Now hold that up against 3i divided by Atlas. We see a coma, a living fog of gas and dust growing and shaping itself in sunlight. We see a tail pushed by light and the solar wind. We see water's fingerprint in the glow, and our best images show textures that match what small, venting worlds do. We do not see clean glints that repeat like a beacon. We do not see straight-line geometry. We do not hear narrow radio whistles that rise above the natural hiss of space. What we see is messy in exactly the way nature is messy. Could a machine hide inside a natural disguise? In stories, sure. In science, we require evidence strong enough to beat the simpler explanation. That's not close-minded. It's disciplined. If a pile of ordinary clues explains an odd behavior, you don't throw out the pile because an extraordinary idea is exciting. You keep watching. You leave the door unlocked, but you don't toss the furniture into the yard. There's another gentler reason to resist the easy sci-fi card. It steals wonder from nature. A comet that wakes early because cold-loving ices crack first is beautiful. A fragile traveler that sings with a swarm of tiny shed pieces is beautiful. A shard from a harsher pantry, carrying a different winter on its breath, is beautiful. We don't need aliens to feel awe. The universe is already writing better stories than we are. None of this forbids curiosity. If someone claims a specular flash, we look. If someone hears a radio line, we check. If a track on the sky kinks sideways, we test our math. But until a signal stands up to every skeptical poke, the bravest answer is the humble one: nature first. So, Hypothesis E lands here. It's healthy to ask. It's wiser to earn. Right now, 3i divided by Atlas behaves like a world of ice and dust under a bright star. That's not a letdown. That's the point. The comet won't wait, so neither can we. Here's the short list of skywork that turns guesswork into knowledge. 1. Watch its breath change with distance. As 3i divided by Atlas moves away from the sun, whose driving should change. If cold-loving ices started the party, the overall activity should fade gently, with fewer of those powder-soft outbursts. If water took the mic later on, the fade might not be perfectly smooth. Little lulls and bumps could appear as sunlit patches wink in and out with rotation. From our side, that means steady light tracking and color tracking over weeks, not just postcard shots. 2. Track the heartbeat. Brightness over time is a stethoscope. Smooth rise and fall suggests broad, even breathing. Small, irregular steps suggest shedding or patchy vents. Fold that light curve on different trial days to sniff out rotation, maybe one long spin, maybe a wobble. If a rubble-piled personality is real, the heartbeat will be imperfect, but persistent. 3. Catch the crumbs. Look for tiny, drifting knots in the halo newborn clumps that separate and fade. They'll smear along the tail and then vanish into it. Even one good catch tells us the surface is letting go of real pieces, not just dust. No crumbs? That's a clue too. Perhaps fragile at the grain scale, but strong at pebble scale. 4. Compare views. Different eyes tell different truths. Sharp space images for structure. Big ground mirrors for faint, extended glow. Ultraviolet to listen for water's echo. Infrared to feel warm dust. Don't memorize wavelengths. Remember the idea. Each window adds a layer, and together they build a face. 5. Test the nudge. Keep stacking precise positions and ask the quiet question: does a tiny push improve the fit? If yes, which direction? Does that direction wobble in a way that hints at rotation? A consistent yes points to lopsided activity. A steady no points to balance. 6. Let time surprise you. Schedule follow-ups after the obvious peak, when many eyes have moved on. Fragile travelers can have late aftershocks, a seam that gives way weeks later, a final sigh of dust, a slow, graceful fade that's more telling than the show itself. Behind all this is a deeper skill: listening without insisting. We don't force 3i divided by Atlas into our favorite story. We ask, and we let the comet answer, even if the answer is both, or neither, or not yet. That's how ʻOumuamua becomes a record. Suppose we end this chase with a shrug at our old labels. Suppose comet turns out to be a suitcase word useful for travel, but stuffed with wildly different outfits. What then? First, we loosen our grip. We teach that comets aren't a single tribe but a crowded city. Early wakers and late bloomers, sturdy bricks and soft loaves, hot-tempered flarers and quiet breathers. The word survives. The borders blur. That's not chaos. That's maturity. Second, we widen our gaze. If interstellar visitors keep arriving with strange habits, we stop treating strange as a flaw. We build surveys that listen for low, early notes. We give time on big telescopes to quiet targets that would have been ignored a decade ago. We let surprise set the syllabus. Third, we grow up about certainty. We don't know yet becomes not an apology, but a promise. In classrooms, we show the draft pages, not just the final diagrams. We tell students that science is a way of paying attention, not a museum of finished answers. Interstellar guests become case studies in how to think, not just what to know. Finally, we remember what these objects really are: postcards from other kitchens. If their recipes are off-book, so are the planets those kitchens bake. That pushes on deeper questions: how seas form, how atmospheres thicken, how often the conditions for life sneak into being. Not what we think doesn't shrink meaning. It multiplies it. Now, flip it. Say the verdict is ordinary in the best way. 3i divided by Atlas is a comet through and through. No artifacts, no miracles, just one with cold first habits and a tender skin. That's still huge. It says our one system rulebook was tidy but small. It says the galaxy prefers remixes. Same instruments, new order. It says we've been standing too close to our own campfire to notice how many ways a snowball can sing. In practice, this just a comet answer gives us a sharper toolkit. We learn what early activity looks like without hand-waving. We learn how fragile skins fool our brightness instincts. We learn to expect handoffs in the chorus of gases as distance changes. We take those lessons back to our own backyard and reread old comets with new eyes. Which ones were whispering early, but we weren't listening? Which light curves were telling us patchy and we called them noisy? And emotionally, it gives something precious back to nature: the right to astonish without needing to be impossible. A strange comet is not a consolation prize. It's a mirror showing us that the universe's creativity runs on familiar physics, arranged in unfamiliar ways, like jazz played on instruments we thought we knew. Here is the quiet gift 3i divided by Atlas brings. No matter which hypothesis wins, a reminder that categories are agreements, not commandments. We draw lines to and help us see. The universe redraws them to help us grow. A small, cold traveler wandered in from a star we'll never visit. It breathed early. It shed softly. It asked us to hold two ideas at once: that the rules are real, and that order matters. That which rule plays first can change the whole song. So we practice a better habit. We give things time to introduce themselves. We let names arrive late. We treat surprise as data, humility as method, and wonder as fuel. And when the visitor leaves, as they always do, we keep listening for the next knock, a little wiser and a little less certain that our map is the territory. Because maybe that's the deepest what if of all. What if the point of a strange comet isn't to answer a question, but to make us worthy of asking better ones? The halo thins. The tail becomes a pale chalk line against a darker sky. Our telescopes blink tiredly and turn to other work. In the silence, the lesson lingers. What if 3I divided by Atlas isn't what we think it is? Maybe it isn't, maybe it is, in a way that makes what we think roomier and more honest. When the universe hands you an exception, you can fix the data or you can change the rule. Tonight, we change the rule just enough to see farther. Tomorrow, we'll do it again.